Okay. This video we will going to determine the we will solve the problem of beam element again, but according to this is the problem from the text of Logan finite element method. Okay, and problem is talking about the continuous beam with at the end of the beam is supported by fixed end fixed support fixed end support. And actually this problem is just like the symmetry problem but for today we will just talking about just only for the case of the general case, as if we not simplify the problem to be the symmetry case. Okay, so according to this, normally we will starting with the first step, that is we have to discretize the element. Okay, so from this problem we will discretize it to be 4 elements. That is for the first one, it's just the element number 1 is just for node number 1 and number 2, right? This is for node number 1, node number 2. We discretize the element that is the to be 4 element because it just like we the node of the node of the system is the same position of the applied load and same position of the support. And according to this, we have 4 elements like this. This third one is a fourth node, and it is a fifth node. Okay, don't forget the sign convention of the beam. Sign convention of the beam for node convention. Node convention. Displacement is upward. Okay, and angle is counterclockwise. It's a positive. Okay. Same as the internal force, same as the nodal force, that is F1, F1y, F2y, M1 and M2 in the same direction. And for this case, the global and local coordinate is in the same direction. Okay, so according to the beam element stiffness metric, let's we may just a little bit review. Okay, for beam element, what is the stiffness K is equal to what? For beam element stiffness is EI over L cube, and then 12 6L, okay, minus 12 6L 4L square minus 6L 2L square 12, okay, minus 6L and also 4L square. Maybe a symmetric case. Okay, by 4 like this. And after we consider each element that is has the equivalent property, same EI, right? And in the same length. Okay, so the element stiffness, it should be equivalent for each element. For each element, it should be equivalent. It's maybe right in this form. It is just the same. And after that, we assemble it together. So we have 5 nodes. We have 5 nodes, right? 1, 2, 3, 4, 5. We have 5 nodes. And 5 nodes, each node has 2 degrees of freedom. So the system is become 10 by 10. Okay, 10 by 10 stiffness. Global equation is become like this. It's just 10 by 10. Okay, it's for 1. If we write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we have 10 by 10 element statement metric, and we have to consider the boundary condition because it is a homogeneous boundary condition. Boundary condition of the support is just defined by the physical meaning of the support. For the support number 1, that is D1 equal to 0 and phi1 equal to 0. And for support number 5, that is D5 is equal to 0 and the angle rotation of the node at node 5 it should be equal to 0 also. And we have for node number 3, we have the displacement at node number 3 equal to 0. Okay, right now actually we don't know that the angle at node number 3 is equal to 0 or not, so we cannot assume that the angle at node number 3 is equal to 0. we not actually we not assume like that. Okay, but for this case actually it is equal to 0 because it is a symmetry case. But right now we just define the boundary condition like this. Okay, so after apply boundary condition by eliminate the column and the row that is represented by this boundary, the system of equation is reduced from 10 by 10 to be 5 by 5 like this. And after that we substitute the value, the given value, that is the applied force, that is 10,000 pounds, okay, into the equation. And after that we can solve this equation. If we know the property of the beam, we can solve it. Okay, and actually for the case that if we know that the it is a symmetry case, for the case that if we know that this is the load is equivalent, so it should be the symmetry case. So it means that phi 2, phi 3 and phi 4 should be 0. So according to this we may reduce these 3 equation, these 3 unknown also. After we reduce, we can reduce this equation again and to be just only 2 by 2. That is the mathematical techniques. It is for mathematical techniques, but it is not the finite element technique. Based on finite element, if we write it in for computer program for solving this problem, it has to solve it directly. It's not simplified. Okay, so just 5 by 5 by computer program is okay. Okay, but if we have to solve it by hand, we may have to use some mathematical technique to apply in order to reduce the system of equation. After that, after we reduce the system of equation, we obtain that the equation is reduced to just only 2 by 2 like this. And after we solve, we obtain the displacement at node number 2 and number 4 is equivalent. The negative signs represent that the displacement it should be downward. Okay, and after we have this solution, we can use for the post-processing, substitute the value, the displacement value, all displacement value into the big one. Okay, we can obtain the force at each node. Okay, you can do it by yourself. And after that, when we substitute it into that system, that big system that is 10 by 10 equation, okay, we will obtain the force, the nodal force of the global system. And the nodal force of the global system represent what? Represent the applied force. Applied force, this is for node number 2. For node number 2 and number 4, right? This is the applied force. This is the applied force that is equivalent to the the force that the problem is given. And for node number 1, number 3, and number 5, this is the reaction force. Okay, you see that the reaction force and the applied force are equivalent. Okay, are equivalent. And for the bending moment, you see that the moment at node number 1, this is the reaction force, is 25,000 pound-foot. Okay, and it's equivalent in magnitude with the moment at node 5, that is 25,000 also, but it's negative sign. Why is negative sign? As we have to consider that it should be follow the positive sign convention, right? The positive signs mean that M1 is in this direction. Okay, that is a positive sign, but this is a negative sign. Negative signs mean that the moment at node number 5, it should be this direction. This is M5. Okay, that is opposite to the positive sign convention. So if we come back to mention the beam problem, you see that the moment at node number 1, that is in this direction, this is the correct sense of the fixed end support, right? That is it should be the negative moment, follow the beam convention. And also for the moment at node number 5, it is in the same. Okay, so the solution that we obtain from the final element, okay, don't forget that it's follow the nodal sign convention. Okay, so according to this problem, actually it is a symmetric case. It is a symmetric case. So we can simplify the problem. We can simplify the problem to be the symmetry one also. And for this solution is for the global force and global moment, the force at node for the global system. And if we would like to draw the free body, draw the shear force diagram, bending moment diagram, we have to determine for the internal force, that is we will obtain the force at node for each element, the force at node for each element. Okay, according to this, we will have the force, the total force at each element. And after that, we have to draw the free body diagram. And we can plot shear force and bending moment diagram. Okay, that's you may have to try to do it by yourself. Okay, to plot the shear force and bending moment diagram according to this problem also. Okay, but it is need to draw the free body diagram and cut free body in order to find the force at each point inside of element. Okay, actually we can solve by the finite element by computer software also, but we will not talking about right now. Okay, we will consider to it again in next clip. Okay, but according to the force, the total force that we obtain over here, we can use it to draw free body diagram and solve for the bending moment at each point. Okay, and actually because it is a symmetric case, so actually we can simplify it to be the simple one. By using the symmetric case, we can simplify the problem from 5 elements into just only 2 elements like this. Okay, let's be okay. I plan to talking about the symmetric case again. That it should be in another clips. Okay, it's not for this clip video. Okay, so I will prepare the problem that is we will talking about the symmetric case again. Okay, this is all for this clip.